Hi, this is Mrs. Rutschling. Welcome to Chapter 11, Ideal Gas Law. One gas law we haven't talked about is the relationship between the number of moles or molecules and volume. This is keeping the temperature and the pressure constant. If we increase the number of molecules, we increase the volume. You could think of blowing up a balloon. As you put more air molecules in it, the balloon volume increases. This is a direct relationship, as you can see by the graph. We're concerned with this version of the law, volume over moles equal volume over moles. And as a reminder, 1 mole of any gas takes up 22.4 liters at STP. This table tells us all in one place the gas law. You can sketch a small graph here, and you can do that for each. Now that we added moles, we put all of these together. It is called an ideal gas law. The ideal gas law is for ideal gases. Remember the kinetic molecular theory assumptions. Those assumptions are holding true for the ideal gas law. You will need to know this gas law. Pressure multiplied by volume equals N stands for the number of moles, R is a constant, and T, temperature in Kelvin. This describes a gas at one condition, and that's how you can tell in a problem if you need to use the ideal gas law or the combined gas law. Taking a look at R, it's a constant, and it's called the ideal gas law constant. The number value is 0.0821. All of this is a unit. You don't have to do anything with it other than put it down as the unit, called a derived unit because it combines others. When you do ideal gas law problems, pressure has to be in atmospheres because we use the gas law constant. Volume has to be in liters. The amount of gas must be in moles, and the temperature must be in Kelvin as always. This problem asks how much nitrogen is required. We have a volume, a pressure, and a temperature. Notice there's only one set of conditions. That tells us we need to use the ideal gas law. The first thing to do is get everything into our proper units. The ideal gas law dictates our units. We have volume in liters, convert temperature to Kelvin, convert pressure to ATM. Once everything is in proper units, substitute into the equation. Notice I don't put any numbers with this. It is simply a very large unit. Solve for N, the number of moles. It didn't ask anything other than how much, so I can leave it in moles. All of the units would cancel except for moles, and I have a value of 1.1 times 10 to the third mole of nitrogen. For sig figs, you want to look at your original problem. There are 2 sig figs, 3 sig figs, 3 sig figs. Since 2 is the smallest, my answer should have 2 sig figs. Pause the video and give this one a try. Solving for pressure, the value is 3.48 ATM. I need to convert it because the question asks for millimeters mercury. So I do that. I have 3 sig figs in my answer because those values all have 3 significant figures. Once again, notice that I don't put anything with this unit. It is simply a very large, cumbersome unit for this value, 0.821. Pause the video and give this one a try. The gas law constant dictates the units, changing millimeter mercury into ATM. Notice I have Kelvin temperature. I've converted that as well. My value is 0.20 moles of oxygen. It asks for grams, so the molar mass is used to change it to 6.4 grams of oxygen.